Hi, this is my prep video or the flip video on 3.81, which is linearization. Now this is a brand new concept, but it's connected once again, it's kind of related to what we have done before. Let's understand the whole idea, right? The whole idea behind linearization is to replace a non-linear function, right, with a linear function. I need to put that. Replace a nonlinear function, right, with a linear function in the neighborhood of a particular x value. Now, what's a nonlinear function? If you take this function, say f of x equals square root x, that's a nonlinear function because x has a 1/2 power. On the other hand, if you look at this function right here, this is a linear function. Why? Because it's a straight line. A linear function is the same as a straight line. You have an x and you have a slope and then you have an intercept. Can you say that right? So what we have really done is we have replaced this nonlinear function by a linear function. Now clearly you can do that always, because if you can do that, then there won't be any crazy functions in the world. All we will have are these nice linear functions. Okay. And but the thing is, we might be able to do this, however, in the neighborhood of a particular point. So to kind of give a visual idea, right? Now suppose you take this graph, you take this nonlinear function, can you see? Like a parabola-like thing, right? It's a nonlinear crazy function. You cannot approximate the whole function by a linear function. Linear function is a straight line. So you cannot really approximate the whole function with a straight line. But if you look at this point, if you select a point and if you look at the little neighborhood of the point, then you can see that in the little neighborhood of the point you can have like if the curve is like that and if the straight line is like that, can you see that the curve and the straight line are very close to each other, right? Near this point, not globally, but locally, you can approximate the complicated looking curve by a straight line segment. So basically what you're doing is you're taking a piece of the curve, right, and near a point you're approximating it by a straight line segment. Now the one thing as students you should know is when we ask for a linearization, and a typical question will be like one of the typical questions will be find the linearization of this function, and then they will give you the point. So you really need to find the linearization near this point. So whatever you do, the final answer should be a straight line function. There should be no f or no x squared or x cubed or any crazy stuff here. It should be just a straight line function. So now how do we actually get to this function? What we do is we take this as I said, you have this thing here. This is our crazy function and this is a straight line. But what is this? This is the tangent line. This is the tangent line to the function at that point. So but we know how to find the equation of the tangent line. We put y minus y1 equals m times x minus x1, and m is the what? The derivative. So it's beautiful. We are really using the concept of derivative to find the equation of this line and then approximate the curve by this straight line at this point. So if you do that, right, then the curve that you get will be this. What is this Lx? It's just a name. You can actually think of Lx as the y of the straight line, right? I mean, so you can think of that as y of the straight line, right? And then this is like the intercept, and this is the slope, which is the derivative clearly, and this is x minus x1. Can I say that, right? Alright, we don't need to know the proof of this, but we really need to know how to apply them. Alright, so now let's go back to our question. We want to find the linearization. So remember, we are asking for what this is actually equation of a straight line. Okay, nothing but an equation. Don't get scared by the Lx, it's the equation of a straight line. So we want to replace this junk by a straight line Lx. Okay, So how do you do? We just look at the pieces of this curve, of this formula, and then plug it in. So we need to find y. So first of all, we need to find f of a, and then we need to find f prime of a. So let's start. Okay, so the function is the given function, the crazy function. So f of x is equal to square root x, right, which is x to 1/2. So let's try to first of all find this piece. What is that piece? That is f of a. So how to find f of a? You just go up here and plug in x equals a. So then we plug in x equals a, then what do you get? For x you plug in a. Now what is a? A is equal to 4. So you plug in 4 here. So you get square root x becomes square root 4, but square root 4 is 2. So we now know what this is. What is that? That is equal to 2, f of a. Alright, okay. So but now we are done with that. We are okay with this. Now let's go up here. We need to find f prime of a. How do you find f prime of a? Well, first we need to find the derivative and then we plug in a. Okay, so we'll start from here. So how do you find the derivative? Well, we find the derivative of x to the 1/2. That will be 1/2 will go forward, 1/2 x to the negative 1/2, right here, and that is, if you take the 1/2 downstairs again as a positive exponent, then 1 over 2 square root x. So that is f prime of x. But we really want to find f prime of a. Now what is a again? A is 4. So what do you do? How do you find f prime of a? You just go to the derivative and then plug in, right, a instead of x, right? So what do you put? You put 4 instead of x, right? So this becomes 4. Then you get 1 over 2 square root 4. Once again, this is f prime of x. You want to find f prime of a, you replace this by a. Alright, so this part. So if you replace the x by a, then this becomes a is 4. So this becomes 4. So it becomes square root of 4. So we have square root of 4 here. And then square root of 4 is actually equal to what? 2. So 1 over 2 square root of 2. 2 square root of 2, and that is 1/4. 1 over 2 square root of 4. Square root of 4 is 2. So 1 over 2 square root of 2 is 1/4. So now we know all the pieces. So we know what this is. F of a is equal to 2. We found that. Okay, we can plug in 2 there. And we know what f prime of a is. And that is equal to 1/4. So we take all those things and plug it up here. This becomes 2 plus what? 1/4 times x minus what is 4? A is 4. So 2 plus 1/4 times x minus 4. So you get 2 plus 1/4 times x minus 4. So if you now distribute the 1/4 inside, you get 2 plus 1/4 x minus 1. Alright, so that is 1/4 x plus, so 1/4 x is there, but 2 minus 1 is plus 1, so you get 1/4 x plus 1. So this is the answer. So once again, look at the answer, just a straight line. It has an x times something plus 1. There should be nothing else in it, no derivatives, nothing. Alright, after we plug in, we end up with a straight line. So always remember the final answer. So what's the philosophy of this problem? So it really tells you that this ugly square root function can now be approximated by a nice linear function by 1/4 x plus 1. So this is like a parabola, right? Okay, and this is a straight line. So does that mean that the parabolas can be approximated by a straight line? Not everywhere, but near the point 4, sure, by this straight line. So if you say select a different point here, then your approximation will be a different straight line. Is that okay? Alright. Let's go to another question. Now here once again how they derive it. Derive the same formula that we give, right? And the derivation is very simple. What we do is we just look at the tangent line. We find the equation of the tangent line. So y minus y1 will be f of a, right? So that's what the f of a comes from, is equal to m is the derivative, which is the slope. So f prime a times x minus x1, right? Okay, so you don't need to know the proof, but that's how you get it. Okay, now let's do another example, guys. Okay, so find the linearization of the function cosine x as equals 1. So once again we have a cosine x, function is cosine x, and we will get, they know what a is. Okay, alright, so now let's find the equation. L of x is equal to this. Now a is equal to pi. So let's find the pieces. First let's find this piece, f of a. So what is f of a? F of a would be cosine of a. So you go up here, you take a equals pi over 2, so it will be what? Cosine of pi over 2. Correct? Which is cosine of pi over 2 is 0. So for 1, this is 0. That's nice. This whole first part is 0. But now we need to find f prime of a. So how do you find f prime of a? Well, f of x is equal to cosine x. So the derivative of f of x is equal to negative sine x. Correct? Okay, so you find the derivative first, and then you plug in a into the derivative. So you plug in x, you replace x by a, which is what? Pi over 2. Then you get what? Negative sine pi over 2. So f prime of a is equal to negative sine pi over 2, which is what? Sine pi over 2 is 1. It's negative 1, so it's negative 1 here. So you plug that in. Alright, so what do you get? You get f of a, we know, is equal to 0. So it's 0 plus negative 1 times, so 0 plus negative 1, so that's 0 minus 1 times what? X minus a, which is what? X minus pi over 2, x minus pi over 2. So you expand this out, distribute this inside, you get what? Negative x plus pi over 2. So that's your linearization. The linearization is negative x plus pi over 2. Once again, you started with a weird function, right? Not really weird, but it's not linear, certainly. Cosine x, right? Okay. And you, bingo, your linearization is nothing but a straight line. Can you see the x and the negative 1 and the intercept? So does that mean that the cosine can be replaced by a straight line? No, but at this, near this point, in the neighborhood of this point, pi over 2, you can replace it by this. So why is this useful? Because a lot of times in real life you get these very complicated formulas, right? And it's difficult to deal with these equations, the complicated equations, right? For modeling certain situations, right? But sometimes it is easier. Life will be easier if you can actually approximate that complicated equation by a linear equation, right? And we, for example, in physics, whenever we have a sine x, right, and the angle is very small, sine theta, right? In optics, right, we approximate that by just theta, which is linear, just x, okay? But we can't do it all the time. We can only do it when the angle is very small. In other words, near 0, we can approximate it. So this is done often when you have an ugly function which happens in nature through a modeling process, and you want to approximate that by a linear function, right, near, in the neighborhood of a particular point. Alright, so that's it for the video on linearization. We'll see you in class.